Okay, let's start with the overview of the problem. The growing power demand due to the establishment of industries and economic growth has increases the load on the transmission and distribution system. As power demand increases, transmission lines are required to carry higher currents, which result in increased line losses and power dissipation due to the limited grid capacity. The traditional aluminum conductor steel reinforced ACSR have a limited current carrying capacity. When high currents flow through, the conductors experience excessive sagging due to the heating effect of the current flowing through it. Limitations of right-of-way made it difficult to construct new lines, particularly in densely populated areas. Thus, any upgrades to the system will require the usage of the existing towers and infrastructures. The topics of our presentation today will cover three types of high-temperature low-sag HTLS conductors that can be used as the substitute of the ACSR conductors, and also maximum ampacity. These are the three types of HTLS conductors that we have chosen. The first one is aluminum conductor composite core ACCC. Second one is thermal resistant aluminum alloy conductor aluminum clad steel reinforced TACSR. And the third one is aluminum conductor steel supported SCSS. Okay, now let's look at the thermal limit of these HTLS conductors. ACCC is capable to carry twice the current of ACSR, and it is designed for continuous operating temperature up to 180 degrees Celsius. It is able to reduce line losses by 30 to 40%. Second one is TACSR, which is designed for continuous operating temperature up to 150 degrees Celsius, while SCSS can operate continuously at high temperature up to 250 degrees Celsius without damage. All three of these HTLS conductors have a higher thermal limit as compared to the conventional ACSR, which is only 90 degrees Celsius, which means that these conductors can handle significantly higher temperatures without significant degradation in performance and physical condition. A higher thermal limit also allows for a higher current carrying capacity, reducing line losses and enhancing the power transmission efficiency. Okay, now the material construction of ACSR conductor. ACSR are composed of a central steel core surrounded by one or more layers of aluminum strands. The steel core provides strength while the aluminum strands carry the electrical current. Okay, now let's look at the material constructions of our HTLS conductors and compare their properties with the traditional ACSR conductors. We start with ACCC. ACCC conductors consist of a carbon and glass fiber composite core surrounded by aluminum strands. The composite core provides the strength and stiffness, while the aluminum strands carry the current. Now its property. ACCC is stronger and lighter than ACSR. The composite core in ACCC offers higher tensile strength, allowing for longer spans between transmission towers and reducing the number of support structures. ACCC exhibit lower thermal expansion and contraction than ACSR. This property reduces the sag in power lines during temperature variations, ensuring more stable transmission. Both ACCC and ACSR have excellent corrosion resistance due to the aluminum strands, but the composite core in ACCC provides additional protection against corrosion, which means that ACCC has a better corrosion resistance as compared to the ACSR. Next, the material construction of TACSR. TACSR conductors incorporate a combination of aluminum alloy and aluminum clad steel strands. The aluminum clad steel strands provide mechanical strength, while the aluminum alloy strands carry the electrical current. Now its properties. The ACSR has an enhanced mechanical strength due to the aluminum clad steel strands, which improve its resistance to mechanical stresses such as tension, vibration, and wind loading. The ACSR also has a better thermal resistance than ACSR, which enable it to handle higher temperatures without significant sagging and reduces line losses. Both ACSR and TACSR have a good electrical conductivity, but the aluminum alloy strands in TACSR conductors maintain the conductive properties necessary for efficient power transmission. Okay, lastly, the material construction of ACSS. HTLS conductors made of aluminum strands from a high purity aluminum or aluminum alloy to provide good electrical conductivity. HTLS conductors have a steel core that provides additional mechanical strength and support to the conductor. HTLS conductors may also include steel support wires that are helically wrapped around the aluminum strands. Now moving on to its properties. HTLS is stronger and lighter as compared to SASR. The steel support wires provide higher tensile strength, allowing for longer spans between transmission towers and reducing the number of support structures needed. The lightweight aluminum strands contribute to the overall weight reduction of the conductors. SCSS also have a similar thermal expansion and contraction properties as SCSR, but the steel support wires assist in maintaining the overall stability of the conductors during the temperature variation, which reduces the sagging effect and maintain the transmission line tension. Okay, now moving on to the costing of the HTLS conductors as compared to the conventional SASR conductor. The first one is SCCC. It is the most expensive among the three HTLS conductors because it has a high performance and advanced materials. It requires a specialized manufacturing process for the composite core construction, which incorporate carbon and glass fibers in an aluminum matrix. Second one is TACSR. It is the second most expensive among three due to it able to withstand elevated temperatures and provide enhanced performance under high load conditions. TSSR utilizes specialized aluminum alloy strands and aluminum collector strands in its construction. The third one is SCSS. It is the least expensive among three HTLS conductors. The reason for which is because typically it has a similar construction to SCSR conductors, with the addition of a steel core to provide mechanical support. SCSS offer increased current carrying capacity and improved thermal performance as compared to SCSR. The traditional SASR is the most economical one due to it has been widely used for many years. It has an established manufacturing processes which lower material costs, and it also has a broad market availability which further lower the cost.
Okay, let's move to the countries that use HTLS in their projects. First, United States Transmission Line. In 2002, CTC Global California has seen rapid development in its hybrid carbon or glass fiber SCCC. More than 1,000 miles of traditional transmission line has replaced with SCCC, resulting in improved reliability and efficiency. So in 2006, the company deployed SCCC for field testing and modified a 6.7 mile length of power line in Utah. By September 2012, the company had installed over 1,000 miles of SCCC conductor wire in over 220 projects throughout the world. So, according to the CTC Global, the use of these conductors can reduce line losses by up to 40%. Okay, that's for the HTLS project that occur in Ireland. So, 80 km of 220 kV gap type HTLS overhead line was installed to increase the capacity of existing overhead lines by 50%. So the improved gap conductor, which is called as GZTACSR, was used in this project. So these conductors can carry up to twice the rating of a conductor of the same diameter it will be replaced. So higher temperatures can be tolerated, which allows for greater power transmission. In 2008, ESBI carried out a design since it satisfied the major technical, economic and acceptable risk criteria for deployment. Okay, let's move on to the four types of heat balance equation. Firstly, the conduction. The conduction occurs when there is a temperature difference between the two materials. When the higher the temperature difference, the more heat will be transferred per unit of time. The transmission line can transfer heat to its surroundings or through direct contact. The amount of heat transferred through conduction depends on the thermal conductivity of the materials, the surface area of contact, and the temperature difference between the objects. So this is the conductive transfer heat equation, which is K play a big role, which is K is the thermal conductivity of the material. Okay, next, the convection. The convection is the process that heat transferred from the transmission line by the movement of fluid, such as air or liquid, flows over the surface of the transmission line. The moving fluid carries heat away from the surface, so the rate of heat transfer depends on the velocity and temperature of the fluid, as well as the size and shape of the transmission line. So this is the equation of the convection. Okay, let's move to the next type, which is the radiation. This process occurs when objects emit and absorb electromagnetic waves. So the transmission line can emit thermal radiation based on its temperature and emissivity, and it can absorb radiation from its surrounding based on their temperature and emissivity. So this is the equation of radiation, which is the QR. So dO is the outer diameter of conductor, and there is emissivity factor, and conductor surface temperature and ambient temperature. For solar heating, this is the process of direct radiation from the sun. The solar radiation from the sun is affected by the solar constant, the angle of incidence, the distance from the sun, and transparency of the atmosphere, and lastly, the surface of conductor. This is the QS, the equation, the solar heating equation from IEEE. So dO is outer diameter of conductor, A is absorptivity factor, and S is solar irradiance, which is the unit is W/M.
To calculate the maximum ampacity, we will use the heat balance equation, which is I equal to square root of QC plus QR minus with QS over with the RT average. So first, to calculate the QC, which is the convective cooling, we will use two equations, which is the QC1 and QC2, and then we'll choose the highest value to determine which QC will we use. To calculate the QC, we need to calculate the mu F, which is the absolute viscosity of air, the rho F, which is the density of air, and the Kf, which is the thermal conductivity of air at T film temperature. To calculate the T film, we need to add the Ts, which is conductor surface temperature, with the Ta, ambient temperature, divided by 2. We also need to calculate the NRE value, which is the dimensionless Reynolds number, to get the QC. So next, we need to calculate the QR, which is the radiative cooling, using the equation given. D naught is the outer diameter and the epsilon is the emittivity. And lastly, we need to calculate the QS, which is the solar heating, using the equation of QS equal to absorptivity factor time with the solar irradiance time with the outer diameter. For the ACSR rate, the RT average, which is the RAC given, is the 9.4 times 10 to the power of negative 5 ohm per meter. So in this case, we need to calculate 5 value of the maximum ampacity, because the given winds, there are 5 given wind speed, which is 1 meter per second, 2 meter per second, 3 meter per second, 4 meter per second, and 5 meter per second. For the QR and QS value is the fixed value. We can use it for each wind speed. And for the QC, we need to calculate a new one each, because in the QC there are NRE equation that use different wind speed. for the ACCC doubling, the RT average at the temperature of 180 degrees Celsius, which is the RAC, is the 8.79 times 10 to the power of negative 5 ohm per meter. In this case, ACC doubling is same to the ACSR drag because we have 5 different value of the wind speed. So we need to calculate 5 different maximum ampacity. So the QR and also the QS is fixed value. We can use it for each maximum ampacity. But the QC, we need to calculate the new one, same as the ACSR just now. So we will get 5 different value of the maximum ampacity. So to summarize, the table show the value of the maximum ampacity for the ACSR rate and also the ACCC doubling, which is the HTLS conductor. Here we can see the different with the different wind speed. The higher value of the wind speed, the higher value of the maximum ampacity. As we can see here in this slide, I used the Excel to generate the graph of the maximum ampacity versus the wind speed for the ACSR and also the HTLS conductor. As you can see here, the maximum ampacity is increasing by the increasing of the wind speed. So we can also see that the value of the maximum ampacity of HTLS conductor, which is the ACCC doubling, is much more higher than the ACSR rate. So for the discussion in this calculation, in terms of the thermal conductivity, HTLS conductor are made up of material with higher thermal conductivity compared to the SCSR conductor. As a result, HTLS conductor may disperse heat effectively during the electric current flow, thus resulting in the lower operating temperature and also lowering the resistance. So the lower working temperature of the HTLS conductor may allow them to carry more current, thus resulting in a higher maximum ampacity. The better ampacity rating as increased heat dissipation will minimize the risk of the overheating. Secondly, based on the construction and material, a steel core like the ACSR is wrapped by aluminium strand in the ACSR drag conductor. So the steel core offer mechanical strength while the aluminium strand conduct electricity. So when compared the steel core with the HTLS, which is the HTLS SCC doubling conductor, commonly HTLS conductor have a composite core such as the carbon fiber or aluminium matrix composite. These provide the better mechanical strength, thus will improve the thermal properties, resulting it will increase the ampacity as shown in the calculation.
Let's move to the conclusion of investigation HTLS conductors. So in the conclusion, the escalating power demand and rising per capita electricity consumption has led to the need for improved transmission and distribution system. So to overcome the limited traditional SCSR conductors, three types of HTLS conductors can be developed, which is we choose that ACCC, TACSR or AW and ACSS. So these conductors offer higher thermal limits compared to ACSR, allowing for increased current carrying capacity and reduced line losses and improved mechanical properties such as higher tensile strength and reduced SAG during temperature variation, resulting these properties enhance power transmission efficiency and performance. So, for the HTLS conductors, it utilizes a composite core construction, providing strength, stiffness, and corrosion resistance. For the ACSR AW conductors, it combines aluminium alloy and aluminium-clad steel strands for enhanced mechanical strength and thermal resistance. For ACSS conductors, it incorporates steel core and support wires to improve mechanical stability and tensile strength. This is 3 advantages of 3 HTLS conductors that we choose. So overall, these HTLS conductors offer superior properties compared to traditional ACSR conductors. So what we can conclude from the discussion, HTLS conductors are made from high thermal conductivity, which is they are more efficient in dispersing heat, and they have generally low resistance and low operating temperature. So the use of HTLS conductors, which can function at high temperatures and with low SAG, has resulted in considerable increases in current carrying capability and resulting higher maximum capacity. That's all from us. Thank you.